Alright, engine startup checklist complete. Now before we request takeoff clearance, let's make sure you're comfortable with the flight panel. Simply put, the flight panel is the aircraft's way of speaking to you and telling you how it feels and what it's doing. Being familiar with the flight panel and knowing what each gauge and instrument displays is key to being able to properly control your aircraft. We will look at the primary 6 flight instruments when we get airborne, but first let's take a quick look at some of the other gauges. Let's take a look over here at these 4 gauges. Primarily the fuel quantity gauge and the oil temperature and pressure gauge. You always need to make sure that you have enough fuel for your flight. Since we just gassed up, we won't need to worry too much about this. However, we will want to monitor the oil temperature and pressure gauges regularly. These can indicate to us if we have an oil leak and will provide us with enough notice ahead of time to avoid any dangerous situations and get us down safely. This gauge right here displays information about the vacuum. If your vacuum fails, all of your gyroscopic based instruments will not read correctly. We'll discuss this more when we actually get flying though. Right here we have the tachometer. This counts the RPMs or rotations per minute of the engine. You're going to want to monitor this and make sure you're never overworking the engine by going over the RPM limit. You can do this by descending and not reducing power. Over here we have the digital clock. The digital clock can tell us our outside air temperature, which is 47 degrees right now, and our voltage. You can switch between this by pressing the button on the top. It also provides a clock, the 12-hour base clock and the 24-hour base clock, and a stopwatch. You can select through these by pressing the select and control buttons. Down here we have the electrical panel. This includes the magneto switches, the master alternator and battery switches, and the master avionics switch. All the various light switches are held down here, along with a fuel pump switch and the pitot heat switch. Right here is the panel light switch. We use this when we need the gauges to be illuminated, and the alternate static air valve, which we'll discuss later. To the right we have the throttle and mixture engine controls. We also have the flap switch, the elevator trim switch, and the 2 fuel selectors and the fuel shutoff valve. Up here we have the radio stack. We'll discuss how to program this later on. I've already tuned it to the Missoula tower, so we should be good. Last but not least we have the annunciator panel and the nav or GPS switch. The annunciator panel will alert you of certain problems that can occur, such as low fuel, voltage problems, and oil pressure problems. Okay, well that should do it for the flight panel. What do you say we get flying? Missoula Tower, Cessna 52 Kilo Alpha, ready for departure, runway 25 VFR to the west.
Cessna November 52 Kilo Alpha, wind is 250 at 6. Clear takeoff, runway 25, west departure approved. Have a nice flight.
Cleared for takeoff, runway 25, Cessna 52 Kilo Alpha. Alright, let's level off here at 4,000 feet and bring the power back just a touch. I'll take the controls and fill you in on what we'll be doing next. If you look right in front of you, you'll see the 6 instruments we skipped over while on the ground. These are the primary flight instruments, which serve as the basis to navigation for both VFR and IFR flights. Among these main 6 instruments are the airspeed indicator, the attitude indicator, the altimeter, the turn coordinator, heading indicator, and the vertical speed indicator. The airspeed indicator, altimeter, and vertical speed indicator are all pitot-static instruments, meaning they rely on the air pressure and air intake information that the pitot tube generates. In icing conditions, it's important to activate the pitot heat switch, which we showed earlier, so that the pitot tube doesn't freeze over. As you just saw, if your pitot tube freezes over, it stops the air intake and pressure readings and renders your pitot-static instruments useless. Also, if for some reason your pitot tube should become blocked, you can use the alt-static air valve to gather air pressure data from another source. Let's take a closer look at these pitot-static instruments. The airspeed indicator uses ram air pressure from the pitot tube to create accurate speed readings. You can remember this easily if you just think about the air being rammed into the pitot tube as we speed up. The speed is read in knots on the Cessna 172 Skyhawk. The altimeter uses air pressure data gathered by the pitot tube to accurately display the aircraft's height. The altimeter reading is referenced off of MSL, or mean sea level. You can read the altimeter almost like a clock. The short needle reads thousands of feet, while the long needle reads hundreds of feet. The vertical speed indicator uses the changes in air pressure to read change rate of climb or descent in feet per minute. When the needle is up, you are climbing, and when the needle is down, you are descending. The other three instruments, the attitude indicator, turn coordinator, and heading indicator, are all gyroscopic instruments. They rely off of a reading from a spinning gyroscope to display the aircraft's heading, attitude, and rate of turn. To understand these instruments and how they work, you must first understand two principles of a gyroscope: rigidity in space and precession. Rigidity in space is the gyro's desire to remain as it is, meaning you can bank and pitch the aircraft any way you want, and the gyro will always try to remain in its original position. This property allows the attitude indicator and heading indicator to give accurate readings about the aircraft's position in relevance to the horizon and magnetic north. Notice that on these two instruments, the aircraft's position is shown as a static, non-moving object. Okay, so let's take a closer look at the attitude indicator. Now as I pull back, we're going to pitch up 10 degrees. How do you know when I've pitched up 10 degrees? You can tell by matching up the orange circle in the wings with the second black line up in the blue section of the gauge. Now, keep in mind that the top blue represents the sky, while the bottom gray or brown half represents the ground. Now, the markings that go up and down between these two sections are in increments of 5 degrees, and they label your pitch. The degree numbers are exactly 5, 10, 15, and 20 degree markings. The attitude indicator also displays bank with the orange upper arrow aligning with the white markings on the outer edge of the instrument. Typically, the first 3 markings on the outer side represent increments of 10 degrees of bank, then it jumps to 60 and finally 90 degrees. Now I'm going to level off here and begin a bank to the left. I want you to think to yourself of how many degrees to the left I'm banking. Do you know how many degrees I'm banking? If you said 30 degrees, then you were right on. Now remember, after this 30 degree mark is the 60 degree mark and then the 90 degree mark. Also, you should keep in mind that the attitude indicator simply displays your aircraft's position in relevance to the horizon. Just because you're pitching up doesn't necessarily mean you're climbing. The heading indicator shows the aircraft's heading compared to magnetic north. Right now, we're traveling at about a heading of 270, or west. The heading indicator shows all heading values as a 2-digit number. This saves space on the indicator, so you should always add 10 to every value mentally. North, east, south, and west are displayed as letters respectively. Their numerical values are 0, 90, 180, and 270 respectively. You can see that the north, east, south, and west headings are all in increments of 90 degrees. The last thing we're going to look at while we're up here is the turn coordinator. The turn coordinator shows the aircraft's direction of turn and rate of turn. It uses the gyroscopic property of precession, which is the tilting and turning of a spinning gyro, to determine the rate of turn. It does this by sensing the pressure on the gyro created by banking the aircraft. Notice that the turn coordinator does not display pitch. The 2 top white markings on the turn coordinator indicate when your wings are level with the horizon. The 2 lower markings indicate when you have achieved a 3-degree bank, or a standard rate turn. At a standard rate of turn, the aircraft can complete a full 360-degree turn in 2 minutes. These are called 2-minute turns. The turn coordinator also has an inclinometer attached to it. An inclinometer shows whether the turn is coordinated or not with the ball. It will show you if the aircraft is either slipping or skidding during a turn, which can be corrected by proper rudder use or adjusting the angle of bank. However, we'll go over this another time.